Hi, everybody. So now let's introduce the tool that we're going to use to prove Lagrange's theorem. And these are called cosets. And basically what we're going to show is that by taking a subgroup of a group and then kind of moving it around inside the group, you can cover the whole group with copies of the subgroup. And so you end up sort of dividing the group up into a certain number of copies of the subgroup, and that's how you see that the order of the group is a multiple of the number of elements in the subgroup. So it's a really nice argument, and it bears thinking about carefully. Okay, so what's a subgroup? What's a coset? A coset is constructed out of a subgroup in the following way. So suppose we have a subgroup of a group G. Doesn't have to be finite in this case. These ideas of cosets work even for general groups. It's only when we start counting them that we're going to care if the groups are finite. So H is our subgroup, and a left coset of H is a subset of G, which consists of choosing a fixed element of G and multiplying every element of H on the left by that element. And of course, since the multiplication is not commutative, it depends that we're multiplying on the left. So I've written that in set builder notation here. We're going to take the collection of products G times H as H runs through the whole subgroup big H. It's called a left coset if the element is on the left. And if you decide to put the element on the right, it's called a right coset. So let's look at some examples so we get a feel for what these things are. Let's start with a simple example where the group is abelian, but infinite. So our group here is the integers, and our subgroup H is a multiple of the integers. Remember that the integers are a cyclic group, and so the subgroups of a cyclic group are generated by choosing an element of the group and taking all of its multiples. So here we're taking n, where n is some integer, and taking all of its multiples. So what are the left and right cosets? Well, maybe just to make our lives a little bit easier, let's pick an n. So to be really simple, let's pick n equals 2. So H is the collection of even numbers. It's -4, -2, 0, 2, 4, 6, ... It's the collection of even numbers. That's what even numbers are a subgroup. To make a coset, we have to pick an element of G, which is the integers. And we have to think about what happens if we take that element and we combine it with elements of H. So suppose we pick the element 1. That's a perfectly good element in G. And so normally here I've written the cosets multiplicatively, but because we tend to write the group law for the integers additively, I'm going to use additive notation. So in that case, we use alternatively the notation G plus H, which is the collection of G plus H for H in H. It's the same thing, we just write the binary operation differently. So I want to take 1 plus H, and that's the collection of things of the form 1 plus H, where H is in H. In other words, take the collection of even numbers and add 1 to them. Well, we get the odd numbers. So 1 plus H is -3, -1, 1, 3, 5, 7, ... So that's one coset, and it's a left coset, but it's also a right coset in this particular case, because of course, whether you add 1 on the left to your even numbers or 1 on the right to your even numbers, you still get the odd numbers. That's because the group is abelian or commutative. Let's look at some other examples. Suppose instead of taking 1 in G, I picked 2 in G. So what's 2 plus H? Well, then I'm taking the collection of even numbers and I'm adding 2 to them. But if you take the collection of even numbers and you add 2, you're just going to get the collection of even numbers back, right? Because you're still going to get even numbers. And if you you can go backwards, so to speak, by adding or subtracting 2. So the coset 2 plus H is again the even numbers. It's the set H again. And in fact, if you think about this for a moment, if you take A plus H, there's really only two possibilities here. You get H again if A is even, because if you take the collection of even numbers and you add an even number, you just shift them, but it's still the collection of even numbers. And it's the same as 1 plus H, which is the collection of odd numbers, if A is odd. Because adding an odd number to the even numbers gives you all the odd numbers. So there are only two cosets of H in the integers. The coset consisting, there's the subgroup consisting of the even numbers, and the coset 1 plus H consisting of the odd numbers. So now we actually have a kind of algebraic interpretation of the odd numbers. They're a coset of the subgroup of even numbers. Just for the sake of maybe looking at one other example, suppose we take n equals 5. Well, then H itself is the multiples of 5. And let's think for a minute about what the cosets are. Well, we know if you let's look at a few. If you take 1 plus H, you get the collection minus 19, minus 14, minus 9, minus 4, 1, 6, and so on. What is this collection of numbers? Well, it's everything of the form 1 plus k times, 1 plus 5k for k and z. In other words, it's an arithmetic progression where the step size is 5 and the initial value is 1. And this is precisely the collection of x and z so that x is congruent to 1 mod 5. And more generally, if we look at r plus h for some r, this is the collection of r plus 5m as m runs through z, right? Because we take the multiples of 5, that's what the 5m is, and we add r to all of them. But that's exactly the collection of x and z such that x is congruent to r mod 5. In other words, the coset is again an arithmetic progression. And we know that these arithmetic progressions, r plus h, is the same as s plus h, if and only if r is congruent to s mod 5. Because the collection of x's which are congruent to r mod 5 and the collection of x's which are congruent to s mod 5 are identical if r and s are congruent mod 5. So, in fact, there's only 5 cosets, and they correspond to the congruence classes mod 5. 0, well, there's h, which is the multiples of 5, 1 plus h, 2 plus h, 3 plus h, and 4 plus h. And in general, if you take a plus h, it's going to be one of these 5. And exactly the same argument tells you that nz has n cosets. And I'm not distinguishing in this case between left and right cosets because whether you add on the right or add on the left doesn't matter. So the left and right cosets in an abelian group are exactly the same. And that's happening here. In a minute, we're going to see where that sometimes does matter if the group isn't abelian. But nz has n cosets of the form a plus nz. And those two are equal if and only if a is congruent to b mod n. So the cosets are the congruence classes. So this is, in some ways, one way you could think of cosets more generally is they're kind of a generalization of the idea of a congruence class for the integers, although things get a little bit more interesting when the group is non-abelian. Okay, let's look at another example. Let's take the group, our favorite non-abelian group, a simple one, S3. And let H be the collection of 3 cycles. So H consists of the identity element, the 3 cycle 1, 3, 2, and the 3 cycle 1, 2, 3. What are the left cosets of H? Well, the left cosets are of the form GH, where G is in G. So what are the possibilities for G, little g? So first of all, if G is a rotation, so if G is in H, then GH is going to be H again. Because, why is that? So for example, suppose for G I picked 1, 2, 3. Well, if I multiply 1, 2, 3 times E, I get 1, 2, 3. If I multiply 1, 2, 3 times E, I get 1, 2, 3. If I multiply 1, 2, 3 times 1, 2, 3, I get 1, 3, 2. And if I multiply 1, 2, 3 times 1, 3, 2, I get E. So multiplying by 1, 2, 3 or by 1, 3, 2 just preserves the rotations. And so the coset doesn't change. It's still the original subgroup. What about if G is a reflection? Well, let's work out what happens if we take 1, 2 times H. Well, we have to do some calculation. So first of all, this is 1, 2 times E. Then it's 1, 2 times 1, 3, 2. And then it's 1, 2 times 1, 2, 3. And let's work these out. So the first one here, this is just 1, 2 again. The second one, so if we're going to multiply here, this is, let's start with 1. 1 goes to 3, and this guy leaves 3 alone. 3 goes to 2, but 2 goes to 1. And 2 gets left alone, because over here 2 goes to 1, but then it goes back to 2. So the product of 1, 2 times 1, 3, 2 is 1, 3. And the product of 1, 2 times 1, 2, 3 is 1 goes to 2, goes to 1, so 1 stays in place. And then 2 goes to 3, and 3 goes to 2 goes to, 3 goes to 1, and 1 goes to 2. So it's just the transposition 2, 3. In other words, the left coset 1, 2, H consists of the 3 transpositions. So H itself, we know this is a group of 6 elements. H consists of the 3 rotations. The left coset 1, 2, H is the 3 transpositions. Are there any other cosets? Well, what if we multiplied 1, 3 times H? Well, we could go through this whole thing. It's 1, 3 times E, 1, 3 times 1, 3, 2, 1, 3 times 1, 2, 3. And it turns out to be 1, 3. Then this product here, we have 1 goes to 3 goes to 1, 3 goes to 2, and then 2 goes to 1, 1 goes to 3. So it's 1, 3, 3, 2, and if you do the last one, you'll see that it's 1, 2. In other words, the other cosets, 1, 2, 1, 3, and 2, 3, they're also the same. They're just the 3 transpositions. So there are just really 2 different cosets. There's the coset H, and there's the coset 1, 2, H. The first one is the collection of rotations, and the second one is the collection of reflections or transpositions. What about the right cosets? This group isn't abelian, so we have to worry about the difference between the left and right cosets. So again, we still have H. That is the same subgroup. But what happens if we multiply by 1, 2 on the right? Well, we still have 1, 2. And now if we do this one, we have 1 goes to 2, 2 goes to 3. So we have 1 goes to 3, and then 3 goes to 1. And if we do it here, we have 1 goes to 2, and 2 goes to 1. So 1 stays in its place. And then we have 2 goes to 1 goes to 3, and 3 goes to 2. So this right coset is again the collection of transpositions. And I won't do all the calculations, but again, it's the case that there are only 2 cosets on the right, H and H12. And these are the rotations, and these are the reflections. So they each have 3 elements. There's a total of 6 elements, and those are the cosets. What about the other interesting subgroup of S3? So what if H is just E and 1, 2? So what is GH? Well, there's several possibilities here. If G is 1, 2, then we have that 1, 2, H is just 1, 2, E, 1, 2, 1, 2. But this is, again, 1, 2, and E, so it's H again. Now we could multiply by the other transpositions, or the other reflections, like we could multiply by 2, 3 times H. And that's 2, 3, E, 2, 3, 1, 2. And that works out to be 2, 3, followed by, and now we have to do this multiplication. So 2 goes to 1, 1 goes to 2, but 2 goes to 3, and then 3 goes to 2. And 1, 3, H is 1, 3, E, 1, 3, 1, 2, which is 1, 3, E, 1 goes to 2, 2 goes to 1 goes to 3. And so, so far we've got 3 different cosets. We have H itself, we have the one which contains 2, 3 and the rotation 1, 3, 2, and 1, 3 and the rotation 1, 2, 3. So unlike in the preceding case where we sort of split up the 2 different types, here they're mixed. The reflections and the rotations get mixed into different cosets. What if we multiply? So these are the ones where you have GH, where G is a reflection. What about the rotation? What if you multiply 1, 2, 3 H? Well, that's 1, 2, 3 E and 1, 2, 3, 1, 2, which is 1, 2, 3. And then here you have, let's see, 1 goes to 2 goes to 3. 1 goes to 2, which goes to 3. 3 goes to 1. So you have 1, 2, 3, 1, 3, which is actually the same as this one. And if you do 1, 3, 2 H, you'll find that it's actually the same as that one. And I think those are all the possibilities. So that, because if you multiply, so there's the identity, there's the 3 transpositions, and then there's the 2 rotations that aren't the identity. And in the end, you just get 3 cosets. And the 3 cosets are the original subgroup, and then 2, 3, 1, 3, 2, and 1, 3, 1, 2, 3. And if you had used, instead of 1, 2, you used 1, 3 or 2, 3, you would get the same picture. I'm not going to do it's a lot of calculations, but you'd get the same picture, but maybe things would be slightly rearranged. But you'd find 3 cosets. All right, what about the right cosets? Well, more calculations here. If we take the right cosets of H, so remember H is E1, 2. So let's take H1, 3. Well, that's 1, 3, because when you multiply 1, 3 times E, you get 1, 3. And then it would be 1, 2, 1, 3, which is 1, 3. And then we have to calculate 1 goes to 3. 3 goes to 1 goes to 2. And if you look back here, it looks similar to the other case, except notice that in this example here, when we looked at 1, 3H, the coset had 1, 3 and 1, 2, 3 combined. Whereas when we looked at H13, the coset has 1, 3 and 1, 3, 2 combined. In other words, these are not equal to each other. And if you do H times 1, 2, sorry, H times 2, 3, that's the other transposition that we haven't accounted for, then you get 2, 3, and you get 1, 2, 2, 3, and you find that that's 2, 3, and then 2 goes to 3, 3 goes to 2 goes to 1, and so on. So you'll notice that, again, here, 2, 3 was paired with 1, 3, 2, but here 2, 3 is paired with 1, 2, 3. So the left and right cosets are different, but again, in each case, you have 3 cosets. I'm not going to do all the calculations because we're going to see for theoretical reasons why this is always the case, but the 3 cosets, they each consist of a transposition and a rotation, either the trivial rotation or a non-trivial rotation, and a transposition. So that's the picture if your subgroup has 2 elements. Okay, so now we're going to actually prove these properties of cosets that came up in this earlier discussion. So what are we going to show? We're going to prove that if you have let's look at the theorem here. If you have a group and a subgroup, then the left cosets of H in that group partition the group. And the partition means that either 2 cosets are equal or they don't overlap, they're disjoint, and altogether they cover the group. Every element belongs to a coset, and therefore exactly 1 coset. And you see this is completely consistent with what we just saw in this example where we took the subgroup with 2 elements in S3. We're looking at left cosets for the moment. You see there were 3 left cosets. They each had 2 elements. There's no overlap between different cosets, and each element of the group belongs to exactly 1 coset. And in our earlier example, where we looked at the subgroup generated by rotations, there were 2 cosets. 1 coset consisted of the rotations, the other of the reflections. Every element belonged to exactly 1 coset. There's no intersection between the 2 different cosets. And in our abelian example, where we looked at the congruence classes, well, we already know that the congruence classes partition the integers into disjoint sets. And so the thing we're about to prove about cosets is just a restatement of what we already know about congruence classes, which is that 2 arithmetic progressions or 2 congruence classes are either the same or they don't overlap at all. And this is true for the left cosets, and it's also true for the right cosets. The right cosets may be different from the left cosets, but they still partition the group, each one, and every group element belongs to exactly 1. So how are we going to prove this? Well, we're going to start out, there's 2 cases. Either if you have 2 cosets, either they're already disjoint, in which case that's good, or they overlap. And what we're going to show is if they overlap, they're actually equal. So suppose they do overlap. So that means there's a K, which belongs to the intersection of these 2 cosets. This K is a group element. And if there's an element that belongs to 2 different cosets, it means that you can write that element as G1H1 and also as G2H2 for different elements, probably H1 and H2 in H. And what does this say? Well, this tells you that G1 is equal to K H1 inverse. But that's equal to G2 H2 H1 inverse. And it also tells you that G2 is equal to KH2 inverse, and that's equal to G1 H1 H2 inverse. And that's just because G2 H2 is K and G1 H1 is K. And we're going to use these 2 equations to show that the 2 cosets are equal, because how do you prove that 2 sets are equal? You show they're included one in the other, both ways. So first we're going to show that G1H is contained in G2H. And to do that, we let X be an element of G1H. So that means that X is equal to G1H for some H in H. But now let's plug in this equation. And that tells us that X is equal to G2, H2, H1 inverse H, which is G2, H2, H1 inverse H. And this is a product of elements in H. So it belongs to H. And if X is of the form G2 times an element of H, it belongs to G2H. And now we can go in the other direction. Namely, we can take X in G2H, then X is G2H for some H in H. And now we use this formula, and we write X equals G1, H1, H2 inverse H, which is G1, H1, H2 inverse H. And again, this is in H. So therefore, this belongs to G1H. So since each coset is G1H is a subset of G2H and G2H is a subset of G1H, G1H equals G2H. So we showed that if we had an element in their intersection, the two cosets were equal. Now we also need to show that every element belongs to a coset, but that's easy to see because G always belongs to GH because H contains the identity element. So GH contains G times the identity element. So every element belongs to a coset. The cosets are disjoint. And this tells us that the cosets fill up the entire group in this nice way. And finally, the one other thing that we observed in our case where the group was finite is that the number of left and right cosets was the same. Now, they could both be infinite, but even in the case where there were finitely many cosets, even though the group was infinite, the number there in the first case with Z, that group was abelian, so this wasn't so interesting. But we're going to actually prove something a little bit better than the fact that the number is the same. Namely, we're going to show that there's a bijective map between the collection of left cosets and the collection of right cosets. So if those two sets have finite number of elements, they have the same number. Otherwise, you could say they have the same cardinality or they're in one-to-one correspondence. So let's let L and R be the set of left cosets and right cosets respectively. And I'm going to define a function from L to R where you take a left coset of the form GH and you make a right coset, but you put the G on the other side, but with an inverse. The inverse is really important. And we have to show that this is a bijective map between the set of left cosets and the set of right cosets. So first, let's show that F is injective. To show it's bijective, we have to show injective and surjective. So to show injectivity, we suppose that F of G1H equals F of G2H. Well, that means that it means that HG1 inverse equals HG2 inverse. And that the only way two cosets can be equal, that means that G2 inverse has to equal HG1 inverse for some H. And now let's multiply both sides of this equation on the right by G1 to get G2 inverse times G1 equals H. And then let's multiply on the left by G2 to get G1 equals HG2. And therefore, we have shown, sorry, I did this wrong. I'll multiply on the left, G2H. And therefore, we have shown that G1 is in the coset G2H. And that means that G1H intersect G2H is not empty because G1 is in G1H and in G2H. And therefore, G1H equals G2H. In other words, the map is 1-to-1 or injective, because if f of A equals f of B, then A equals B. To prove that it's surjective, we have to show, so let's let HG be any right coset. And then we have that f of G inverse H, which is a left coset, is by definition HG. So f is surjective because every right coset can be gotten by applying f to a left coset. And this shows that our function is bijective, and so there's a 1-to-1 correspondence between the left cosets and the right cosets. And therefore, if the number of left and right cosets is finite, the number is the same. So left cosets and right cosets each have this property that they partition the group into disjoint sets. The number of elements in those partitions are the same, but the individual cosets, the left cosets, may not be identical to the right cosets. So if you're working with a non-abelian group, you can work with left cosets and do most things that you want to do. You can work with right cosets and do all the same things, but they're not, the left and right cosets aren't identical. So we're going to use these ideas of cosets to finish the proof of Lagrange's theorem.